Okay, let's start. So today we're going to move back to jets, and we talk about the calibration sequence for jets that is applied in the Atlas experiment. Is very similar to what is done in other experiments at the LHC, especially in CMS. It's not very far away, but before we do this, I want to catch up on the particle flow signals, which I didn't have the time to talk about last time because I spent too much time on telling you about the signal formation in the liquid argon calorimeter, which I find an interesting little project. Just a quick recap, we talked about the signal shaping. This is a hardware solution of to suppress pileup as much as possible and overcome the challenge of the long charge collection time that we have on the liquid argon calorimeter. Basically, what we do is we apply a rising signal shape, which is sensitive to the initial current and has a peak amplitude that corresponds to this current, and that can be translated into an energy. The triangular pulse coming out of the detector is, in this context, converted into a bipolar pulse, which is net zero integral, which means that the out-of-time pileup cancels the in-time pileup contribution on average. This works only within some limited precision, mostly because pileup is, of course, subject to fluctuations. And we apply also a topological cell clustering, where we basically find groups of cells that have that follow certain signal significance patterns. I have to fix a few things on the slide after this. It's basically a seed and growth algorithm, which we talked about in quite some detail, which after you have collected all the cells, you probably have to split between local maxima to be to not merge too much energy in one direction. So you're getting insensitive to jet structures and stuff like that. You want to have the highest possible flow resolution that you can get in terms of directions and the energy. And the shapes of these clusters and their location support to apply a local calibration sensitive to the nature of the cluster, which is expressed by an electromagnetic likeliness measure, probability. So we have these clusters now, and now it's time to form jets. Oh no, it's not yet. We still have to talk about particle flow. So particle flow is a concept that CMS has implemented right away. In Atlas, we had early solutions, but it has only in the last few years gained stability and performance, so we can actually use it. The idea is that for charged particles only, you remove the calorimeter signal of these particles if a well-measured reconstructed track is pointing to it. And the judgment is purely made on the ratio of the energy over the diameter of the track. They should be close to each other. If the calorimeter is well calibrated, you would expect 1. You get values around that number for if you apply the calibration. But we also implemented partial signal removal, so we don't necessarily require that the track hits just one topological cluster and removes it. We can also do partial removal, and we will talk about this a little bit. The good thing about this strategy is we have the tracks have a vertex association, and we can find the tracks that come from the hard scatter vertex. This is, of course, an assumption, and it's not true for all final states that the underlying vertex assignment always works 100% efficiently. But it has the advantage that we can actually find the signal coming from the hard scatter and not from pileup. On the other hand, we can use the tracks from pileup vertices or the other vertices, which point to pileup generated calorimeter signal, topo clusters, and then can remove these clusters. So we can use the tracks to remove pileup from the calorimeter. There's a clear limitation that we have only tracking up to rapidities of 2.5. And the range of tracks that are useful for this exercise is 500 MeV up to roughly 100 GeV or so. The matching algorithm is quite complex. It cannot be done, cannot be redone typically during a run year. So it's done once because it needs very detailed information on the calorimeter signal, including the calorimeter cells, which are way too many to write out for physics analysis. So we only can do this really well then to write the particle flow objects out, which are the result of this matching. So the way this works, if you look at a simulated event here with tracks and clusters in the eta phi plane, this is just one sampling of the calorimeter, the second sampling of the central barrel calorimeter in Atlas. You find the clusters, which are the shaded objects. And then you find tracks that belong to that in purple and tracks that come from elsewhere in yellow. And you can associate in red, those are the cells in the cluster that are associated with track. The green marked cells are associated with neutrals. This you know, neutral energy deposits, this you know because it's a simulation. And the blue ones are if you do particle flow, so this is the starting point. If you do particle flow, you remove a lot of clusters, as you can see, and the whole situation becomes a little bit more cleaner. There's still pileup surviving. For example, here you see still blue dots. Here's a lot of blue dots. And of course, inside the cluster, there are blue and green dots mixed, sometimes even red, because pileup enters the cluster also just in the form of some cells. So it's not necessarily the case that pileup generates a cluster. You see that the track match with the cluster can actually poke little holes in our cluster, and here, and some here. But it removes a lot of things that do not belong to the hardscatter final state. So the matching, you can think about many scenarios actually. The most obvious golden matching, as we sometimes called it, is if the track hits exactly one topo cluster and removes it. The judgment for this comes from the fact that the cluster energy is very close to the energy we expect from the calorimeter to be reconstructed from the calorimeter for a track with a momentum P. This is just measured by this E/P ratio, which is done with isolated events, typically at low pileup. So we have a very clean relation between the calorimeter response and the track. Sometimes you cannot remove, you should not remove the whole topo cluster, so the calorimeter signal may be considerably larger than the expectation from E/P. In this case, what happens is actually cells around the track are reweighted in their contribution to the cluster, where the cells closest to the track have a weight of 0, so they're basically removed. And then you have concentrical rings, in which this weight goes up to 1, back to 1 again. So the cells furthest away from the track have a weight of 1, they're not touched, they stay with the cluster. And we have complex cases, of course, you can match one track with 2 clusters, 2 tracks with 1 cluster, and so forth. The particular removal strategy depends on the signal expectation that comes from the track. So there's actually on one of the first pages of this talk, I have the link to the paper which discusses all this in great detail. And I really don't have the time to go through this, but it's an interesting algorithm and it's now well tested. Why do we want to do this? Well, we jump ahead and look at the energy resolution for jets reconstructed with the Atlas experiment. Here's simulations. You see 4 kinds of jets here. The black ones are particle flow jets with pileup. The green ones are particle flow jets without pileup. The red ones are just calorimeter jets without pileup, and the blue ones are calorimeter jets with pileup. And you see that at low transverse momentum, the resolution degrades significantly if you use only the calorimeter compared to the use of tracks in addition to the calorimeter. There's still a dependence of the particle flow jet on pileup, because the particle flow jet is made out of charged particle flow objects, which are basically tracks, and neutral particle flow objects, which are the remaining clusters or fragments of the clusters that have not been removed. What is clearly visible is that the spatial resolution is significantly improved by the particle flow method. That was expected. The tracks have an excellent spatial resolution. So you see this reaches even to energies of several hundred GeV. There's still an improvement visible. So this is certainly something we should do, and we are doing it now routinely. So we're using the particle flow signal for a routine jet finder. You're always worried about efficiencies. If you look at the jet reconstruction efficiency, that means the likelihood to reconstruct a true signal jet. If you do the calorimeter only is the blue, and the particle flow jets are the green. If you apply a pileup suppression to the jet, which we will discuss actually next time, this is an old style. There's no newer methods, but I couldn't find a newer plot. You can see the jet reconstruction efficiency drops by about 0.5% or so for the calorimeter jets, while in the particle flow jet, and in this particular study, didn't have any additional pileup suppression, but in general, it's very stable against pileup. This you can also see in the plot on the lower right, which gives you the number of vertices reconstructed in the event, which is a good measure for in-time pileup, and the number of jets coming out of this. Of course, your physics should not depend on the number of vertices you have in your event, number of pileup vertices. So it's not good that the calorimeter jets rise, that there are more jets produced when the number of pileup interaction goes up. But it's certainly encouraging that after applying the JVF correction, you can mitigate this rise even with the calorimeter jets only. And it's for the particle flow jet, it's already quite flat. So we have very little extra jets coming this way if we use the signal. So clearly there's a nice stability to this. Actually, the plot on the lower right really compares data and Monte Carlo. So you see that we also have, for the calorimeter only jets, for example, the modeling is not exactly great. And so is actually for the other jets, the modeling is also not that great, which relates to the fact that we really have problems to model the pileup, which we talked about some sessions ago, at least a little bit. So let's move to the more important part, meaning the actual reconstruction of jets. What I'm mostly discussing in this context is actually the calibration of the jet. We have talked about the jet finders. We have talked about the input signals. So there's really not much more to say about the reconstruction. Let's just look at the sequence with which we calibrate our jets. So in Atlas, we have two major classes of jets. One is the standard small R jet, as we call it. It's an anti-KT jet with a distance parameter of 0.4. It comes with, as said, with two choices of input signals routinely these days. We have the calorimeter only jet formed from topoclusters at the electromagnetic scale. And we have the p-flow jets, which is a mix of the charged p-flow objects and the neutral p-flow objects at the electromagnetic scale. We use full momentum recombination in the clustering of the jets, as has been agreed on for a long time ago. So the first thing that happens before you even find jets, you shift all the inputs to such that the direction comes from the particke. This doesn't change the signal, but it changes the direction associated with the topocluster. Of course, for tracks, we don't have to do this. The tracks have a well-measured direction coming. The tracks from the hard scatter vertex have a well-measured direction already, so there's no shifting needed. So the sequence you see here is actually the one for calorimeter jets. So this gives us we then apply the jet finder to the now shifted topoclusters, and we get the jets on the EM scale, either, again, the calorimeter jets or the p-flow jets with the neutral objects on EM scale. Then we have to get rid of the pileup. So we already talked about the jet area-based pileup correction. That's the first thing that is applied. but it's not sufficient, and we will look into this for just a little bit. So we need another residual pileup correction that comes from simulations. So once we have done that, and the jets have still sufficient transverse momentum after all these corrections, we apply a Monte Carlo-based calibration. That means we have derived the calibration using simulations. We'll talk about this a little bit more too. After that, we do a refinement of this calibration, which we won't talk too much about, but it's basically the idea here is to use other information about the jets to correct the energy a little bit and mitigate some dependencies on the fragmentation of the jets, meaning where does the jet come from? Is it a heavier quark? Is it a gluon? Is it a light quark? These things can be mitigated at least to a certain degree in this step. And once we have done this, we have jets that are now fully calibrated using only Monte Carlo, basically only Monte Carlo information, except the little yellow box here. The jet area-based pileup correction is, of course, using energy densities in the data in the Monte Carlo separately. So we have to make sure that at the very end, the applicability of the Monte Carlo calibration is measured to the data. So the applicability of the Monte Carlo calibration to the data is measured, and if there's any correction to be done with our residual in situ calibration, which is only done applied to the data. It's not applied to the Monte Carlo. The Monte Carlo is calibrated after the global sequential calibration. So all simulated jets are calibrated after global sequential. The data jets get another final step to shift them to where the Monte Carlo jets are in terms of the response scale. So here's what I said. I'll leave it to you for later to read again. The in situ is characterized by two steps, if you want. There's a so-called eta intercalibration. Its name is historic. We really should call it rapidity intercalibration, but I think it's now in our heads as eta intercalibration. This corrects for the for some differences in the data in Monte Carlo response as function of the direction, the calorimeter, and it does it with respect to what happens in the central region. And that's which sets the scale for the central region, which uses well-measured objects that are not jets, like photons or Z-bosons, and balances those with the jet or jets, depending on which final state you're looking at. Photons and Z-bosons cannot be used at very high energies anymore. Have very high energies, we do actually a multi-jet balance, which means we balance a very, very high energetic jet with a group of lower energetic jets that are already calibrated. So we're looking for very particular topologies where this balance can be applied. We have also larger jets. So those are clustered with a distance parameter of 1. At the time, they're routinely done right now only for using calorimeters for analysis. At least they're routinely done only using the calorimeter. And they're also using the calibrated, harmonically calibrated cluster, so we call them LC topo jets. Like the smaller, we're using 4 momentum recombination. We are working on getting the and commissioning the LCP flow jets in the context of the larger jet, but this is not yet at a stage where it can be used routinely. So the larger jet is slightly different than reconstruction, and calibration sequence is slightly different than the one for smaller. So we start with the clusters on the LCW scale. They are again shifted to the actual event vertex, so their direction is already corrected. We reconstruct the jet, and then we have what we call an ungroomed larger jet at the LCW scale. The problem with larger area-based pileup suppression, because the assumption that the pileup density is constant inside the jet is simply not true anymore for larger jets. the variation of the transverse momentum density as function of rapidity in such a large object is significant, and we were not able to get a well-performing jet area-based correction going. So we use other techniques, jet grooming techniques, where we remove soft parts of the jet, which more or less automatically removes pileup contributions. Once we have the groomed jet, and the most famous grooming we use is trimming, but we will talk about this next week. Anyway, so we have the groomed jets still at the calorimeter energy scale, calibrated energy scale, and then we do a calibration with respect to the energy, the direction, and the mass of the jet. Why do we want to do this? Larger jets are typically tools for searches for new particles decaying into a larger jet, where the mass is actually has a significant physical meaning compared to smaller jets, where the mass is very model dependent and comes from the Monte Carlo alone. We have to do a residual in situ calibration to larger jets as well. And after that, we are fully calibrated larger jets for the analysis. The residual is very similar to the one that is done in smaller jets. It just takes care of the final residual differences between data and Monte Carlo. Okay, here's what I said. I mentioned the trimming. This is the way we groom our jets. We will talk about this next time. So let's go talk about itself. So the simulation-based calibration, we need to establish a truth reference for our reconstructed jets, detector jets. So what we do is in the simulation, we take a truth particle jet, which is clustered using the stable particles that can reach the detector. And we match it with a simulated detector jet. And we then can calculate the response of the detector jet, let's say in the calorimeter, either at EM scale, or we could use the calibrated hadronic scale, divides this by the truth jet energy, and we get the calibration as function of the truth jet energy and the direction of the jet. Then we apply a little trick, which is called numerical inversion. I have a few extra slides at the end of this. I really don't have time to go through this. That tries to explain what happens in numerical inversion, just to show that the response function stays more or less a Gaussian. And then from this, you get the calibration function by inverting this response. So the matching criteria are sketched at the bottom of the slide. There's basically isolation requirements for the truth and for the detector jet, and only very clean matches are used to calibrate the jets. If we look at the jet area-based pileup subtraction, the first step before we can actually go and apply Monte Carlo calibration, we have a problem in Atlas in particular. If you look at the distribution of the average momentum density as function of rapidity, which we showed in lecture 3, in the detector, if you look at the right figure, it looks very different. And the problem of why it's so different is related to the fact that at rapidity of 2.5, negative and positive, beyond that, our detector granularity drops, decreases by a factor of 4 at least. So on the left, I actually show you a picture of the number density or relative number density of topoclusters as function of the rapidity, and in blue is the granularity of the cells. So you see actually how the topoclustering follows what the cells do. There's a hard cut at 2.5, and this makes the row measurement in the forward region really hard, or actually it's impossible. The median concept shifts a lot of the values to 0 in many events. So we had to do something else. So what we do is first we do the jet area based correction, and you can see the effect of that as function of rapidity in the left plot. So we start with the blue, that is the PT per vertex that is added to the transverse momentum per vertex that is added to the jet and that we want to get rid of. This is just added by pileup. And then if you look at the purple, that is if we only do the jet area based, which works very well up to about rapidities, jet rapidities of 2 to 2.5. And then there's basically no effect anymore. We still have a quite a significant rise of pileup contributions in the jet. But then we developed a Monte Carlo based technique where we have two parameters that allow to apply correction based on the number of vertices, the in-time pileup, where an MPV -1 is used because if you have one vertex, it's a hard scatter vertex. And we have another factor beta, which takes care of the out of time corrections that are needed. And the two plots show the different effects of these corrections. You also see what is interesting, maybe that at higher rapidity we are losing transverse momentum in the signal jets due to the out of time. So we're overcompensating pileup, in-time pileup somewhat. That's kind of an interesting fact. Now we did this. We developed these Monte Carlo corrections. You see the red is basically flat at 0. So this works very well, but it is model dependent, and we have changed the concept for run 3 a little bit because there are actually this formula doesn't assume any correlations between the number of primary vertices and the number of interactions, the average number of interactions, which is mu. So to fix that problem, we have now a better formula, which is not yet public, I think. So I didn't want to show it, but if you have access to the slides of the specific meetings, you can see it. Okay, so once you do this, you have a pileup corrected jet, and now you can apply some further corrections. There's a Monte Carlo based direction correction, which is just reacting to the fact that the calorimeter has cracks in its structure, meaning we lose energy in dead materials around 1.4 and 3.2. This are the most significant ones. And that actually pulls the jet either further forward or more central. The direction of the jets going in this crack direction is not very well measured, but we have developed a Monte Carlo based correction to take care of that. This is not the general shift to the vertex. That is something that happens independent of this correction. Then we do the jet energy calibration as described, and you can see in the lower row of plots, you see actually the energy responses on the various jets on the various energy scales. So the left one is the electromagnetic energy scale, and if you look at low energetic jets, which only have like 30 GeV or so energy, you can really only see them in the central detector because we apply a selection based on the transverse momentum of about 20 GeV. So the further you go out, the less of those jets will survive. But you see that we need correction factors larger than 2 to get the red points to 1 where they're supposed to be. So with energy rising, these correction factors get smaller. Of course, if you go to particle flow, you have now a good part of the jet are reconstructed tracks, which are basically a representation of the true particle energy momentum with some mass assumption. And here we're getting the response gets closer to 1, even if we use the remaining topo clusters at the M scale. So the corrections you need here is certainly much less than 2 even for the red points, which are again the 30 GeV truth jets. If you look at the larger jets and you look at the locally calibrated clusters, you see that the response is actually pretty close to 1 already. You're looking at about 5% or so outside of the cracks that is missing. So this is an effect of the local calibration. It really shifts the clusters already close to a useful scale. And that's why we continue to use the locally calibrated cluster also for measurements inside the jet. Again, something for next week. We have a mass calibration. I don't want to go through formulas in the smaller jets. This is my latest knowledge, but we can correct the jet mass as well. For larger jets, it's applied by default. It makes a lot of sense. The opening angle of the jets is large, so the mass is an observable of importance also in the context of searches. The response, I hate to say mass response because it's a calorimeter, it doesn't respond to mass, but okay, let's call it the mass response because everybody else does it, is with Monte Carlo is measured using the true jet energy and then the ratio of the true jet mass over the true jet energy and the direction of the jet. The log of this ratio, this is just to keep the reconstructed mass minus truth mass distribution as Gaussian as possible. And from this you can get a calibration. The calibration is applied such that the energy of the jet is not changed anymore. The calorimeters measure energy. We have done everything we wanted to do to the jet to correct the energy. So we don't want to invalidate all previous calibrations and all previous grooming steps and whatever we did. So this actually only affects the jet transverse momentum, which is okay because we do an in situ calibration where we basically correct again the transverse momentum scale such that it's the same in data in Monte Carlo. So the energy is not touched, the mass calibration is folded into the construction of the transverse momentum. So if you look at the so-called mass response, that is the mass of the detector jet over the mass of the truth jet, these are now trimmed anti-KT R equals 1 large jets. And you see that the for relatively low momentum, these jets have a nice, this is uncalibrated response, so they have a nice measurement of the jet mass already. But the higher you get in transverse momentum, you see interesting shapes coming up that also seem to somewhat be related to detector features. And of course, there's also the other effect, which means that if the momentum gets very high, the energy of the jet gets very high, you probably have some effects of having several particles contribute to just one topocluster. Things getting a little, the core of the jet gets actually a little narrower. So there's all kinds of effects that fold in. And you can see the shape of these functions, of these responses, depends on actually which window of mass you're looking at. So the left one is at about half of the W mass. If you go to the W mass, there's clearly a change. But the higher energies respond at higher energies, at higher momentum, transverse momentum, the response is a little better. It gets closer to 1. And if you go to like the top mass, you see that the low energetic jet, if you only have 200 GeV, seems to not respond very well. But that is expected because at 200 GeV, the jet cone of 1 is actually too small to fully capture the top inside the larger jet, and we will talk about this again next time. You typically need about 350 GeV to more or less fully capture the top decay into a larger jet of the size 1. So the in situ jet calibration, which is now last point for today, and the one that is only applied to data, it accounts for jet response differences in data Monte Carlo simulations. There can be a whole gang of sources for that. Imperfect detector descriptions in the Monte Carlo, simply not knowing where exactly the detectors are with enough precision can already be a problem. Then the simulation itself of the electromagnetic hadronic showers has certain weaknesses and inefficiencies, especially in the hadronic sector. Then, of course, what enters also are all kinds of modeling aspects. So the fragmentation of the particles from the hard scatter, the underlying event, the pileup, can lead to a appreciable differences between data and Monte Carlo. The general recipe to address this is you take a well-measured reference object, which is not a jet. So let's start with that. Let's say you look for photon plus jet final states, and you calculate the response ratio of the probe jet in terms of to the transverse momentum of the reference. This we call direct balance. Another option is you can actually project the reference. Oh, I'm sorry, there's a ref there. There should be a jet there, I think. You can actually calculate the missing transverse momentum vector in the transverse plane of the event and put your jet transverse momentum on that. And this is called the missing projection fraction. I have to fix this formula. I have to remember that. Which gives you a nominal response of the whole system against the reference object. So, for example, no, I'm sorry, the formula is correct. The ET miscaptures the response of the jets. I'm sorry. So the reference, the RMPF gives you the whole response of the whole final state against the reference object. So you have to do a little bit of gymnastics to get the jet response out of this. And I can only point you to the papers. This is a long story. Anyway, having done that, you construct a double ratio, basically the either direct balance or the MPF, where you compare, where you divide the observation and data of the ratio by the corresponding ratio in Monte Carlo at a given scale. Typically, you start with the reference scale, the photon Z boson scale, and then you can extract the calibration, including again the numerical inversion step, which allows you to get these functions at the scale of the jet. So what happens with this is you get a factor which describes the difference in the jet response between data and Monte Carlo, because the idea is that the reference PT is measured at very high precision, meaning it compares very well between data and Monte Carlo. There's a whole slew of things that can enter this this strategy. We will talk about this when we talk about systematic uncertainties more. But the interesting thing you should remember is that this ratio of the reference PT and the jet PT, there's no reason for it to have a central value of 1. Because you have radiation patterns, you have other losses of energy. The jet finder may not capture everything. So there was, for years, there was a very weak theoretical understanding what this ratio actually is supposed to be. So we don't really rely on this. We just select our events with the same topology in data Monte Carlo, and then see what's this. We are not interested in the absolute ratio. We're only interested in the double ratio of the Monte Carlo data. So this the ingredients of such a selection are shown here. So you basically have in the left upper part, you have a Z boson or a photon with providing us with the transverse momentum reference. And you have the jet you want to test, the big J1 here. But there's certainly very likely also some radiation in the event, so that we have enough phase space to have a second or third jet. So you have that. And you can study this, for example, you can study this ratio as function of the momentum of this, of the transverse momentum of the third jet, of the second jet. You can study it as function of the opening angle between the momentum, the transverse momentum of the reference and the jet transverse momentum. So you have to do all these studies and see how this ratio develops, both in data and Monte Carlo, to determine the uncertainty of this. The sketch at the right shows you what happens if you apply a multi-jet balance, which uses a system of well-calibrated jets and balance it against our probe jet J1. So with all these methods have validity within kinematic validity, regions that actually go quite high now. We started with photon jet. I remember the limit was about 300 GeV, but now we're up to 1.2 TeV. It's largely a cross-section problem, so it's largely statistics that hindered us from reaching that far. Now we have many more events, so we can actually do this. Z plus jet doesn't reach quite as high, and the multi-jet balance starts around is useful around 300 GeV up to about 2 TeV. Now we have higher momentum jets, so we typically apply fixed calibration to those because we're losing reference. Okay, I said that's time. Carrying on. The one thing that is done slightly different is actually the calibration. So this is done with dye jets, and it's a first step in the in situ that we actually do. It's the idea here is that you take you compare the response of a forward-going jet with the response in the central region, and once you have done that, you can calibrate the central region using the photons, Z bosons, and the multi-jet final states to get the absolute scale. And I hate to say that because it's really not the absolute scale, it's the Monte Carlo scale that we're calibrating to. But anyway, you see there's quite large variations in the relative jet response between data and Monte Carlo as function of the rapidity. It's flat in the central region, partly by, I mean, that's actually the good side. But there are significant differences which have to be corrected before you can claim that you have calibrated your forward jets as well. And unfortunately, there's a lot of model dependence in these differences. So you see two different generators here, our standard workhorse, POWEC and Pythia and Sherpa. And yeah, it's simply not, it's still a source of relatively large uncertainties applied to forward jets. So if you look at the somewhat cleaner transverse momentum ratios for photon jet, here, for example, we compare two methods. One is the direct balance and one is the MPF, and also two different signals. We have the calorimeter only and the P-flow with several different generators. You see the black points are the data, and the green, the blue and red points are the two generators, fully simulated final states, of course. And you see that the ratio is kind of flat as function of the PT of the jet, and it's about 2% more signal in the jets for Monte Carlo than in data. So we can correct this. We can use these ratios to, and here's another example on the dependence of the final state choice, but this is not so important. So let's move on. So we can use these double ratios now to develop or to extract calibration functions. We usually do this with respect. I need another 2 minutes, but then I'm done. So we need to do this with respect to the nominal, what we call a nominal Monte Carlo, which in our case is POWEC and Pythia 8. This ratio reflects where we want to be with our data jets. So it's a typically 2% difference, so it's a small correction. And the interesting part of this is if we calculate this calibration function on slide 29 here, we have now these three different final states that we can use, including folding in the methods. We even have more room. But we combine those to one function, and we use weights which are larger, the smaller the uncertainties are on a given method and on a given final state. So we use always the final state that is the most precise evaluation of our transverse momentum ratios, balances. And this looks like this. This is actually the relative weight in the combination. And you see that at very high energies, we only have multi-jets left. But you see it has some interesting shapes, this weight, but it's purely coming from the precision that we can do the individual balance measurements. So once we know that, and this is really the last thing we talk about, or the last thing we see today, we can get these nice functions. You have to be there's a little bit of smoothing involved, just numerically local smoothing. And you can see that these functions are the response, the ratio of data to Monte Carlo. So if we invert those, and we Monte Carlo-based jet calibration, plus the in situ correction. I'm sorry, should be careful. So we do this for P-flow jets in the upper right and for the calorimeter jets in the lower right. And then you also see that we do it for larger jets, and you see that the green and red bands are the errors. We certainly have some problems at very high energy larger jet statistics, but you see that the calibrations are not very different for smaller and larger jets. So this is the result of a lot of work and a lot of trying to understand what's going on in the detector for these jets. So we have a very precise jet measurement in the end. Okay, so this was where I wanted to be today. Sorry, I had to speed up a little. I want to really focus on the performance and systematics tomorrow, which is a little more complex again. So I think you can take these slides home and look at them more carefully, and go even find some papers where these things are probably not explained in great detail, but at least you see the latest results. Are there any questions? You have a question?
Can you hear? Excuse me, can you hear me?
Yeah, I hear you.
Okay, thanks. Because your sound sometimes chop. So my question is, when you mentioned when you calculate the response function, right? You have to match a truth jet to a recall jet, and I wonder, does it occur sometimes that, especially in a low PT regimes, that you cannot assign one-to-one each recall jet to a truth jet? Can that happen, or it barely happens?
No, it happens. One of the problems is, if you think about the calorimeter jet only, at low PT, you have a lot of, the charged particles are curved a lot by the magnetic field. So the calorimeter jet, maybe in a slightly different location, where the truth jet, which is not affected by the magnetic field, where the truth jet is. So we do this by increasing the matching radius a little bit. I think now we actually have a fixed radius of like 0.4. So it's a very generous matching radius. It's not very small. Let me see if I find it quickly. There's a little drawing is here. So if this R match is pretty big to make sure that we don't lose efficiency in our truth jet matching. But we still apply rigid isolation criteria, but the matching radius is quite big and accommodates most of the effects from the magnetic field at low transverse momentum.
I see. And then you mentioned the kind of the identification. I remember in my memory, if my memory is correct, if I read some round one paper, there was some discussion about, jet reconstruction efficiency, but I didn't see such a kind of term in round two. So does it mean that this kind of problem basically was resolved in round two?
I'm sorry, what problem are you referring to? Can you repeat this, please?
Yeah, so like for electrons and muons, we always have the identification efficiency, but it seems that at least in round two, I didn't see identification efficiency for jets. So does it mean it's because the generous matching you mentioned? So basically, we don't have this problem anymore.
No, I mean the matching efficiency is only needed when you calibrate, when you develop the calibration system, right? When you measure the functions, when you determine the functions to be applied. Once you have them, they apply to any good old jet, of course. And what you're still interested in is, of course, after you do this, you're still interested in the efficiency of the jet finder, and that may may have the same or another matching. I actually don't recall how this is done. These things don't need to be the same. They don't need to have the same matching radius or the same matching strategy. I mean, I remember that in some times we discussed something that's called a ghost particle matching, which means that you take the truth jet 4 vector and you just add it as a ghost particle to the experimental final state. You find your jet and see if the truth jet 4 vector made it into your jet. And then it was called matched as well. So you have several options, especially in the physics context of efficiencies. You probably can also think about final state influences in different analysis. So you probably want to check this. But there are several pieces of software on the market to do that. For the calibration, we have a fixed rule because this needs to be somewhat controlled. And it's always using the same final state, which is just a dijet. So the jet efficiencies are mostly affected by pileup, actually, by the effectiveness of the pileup correction.
Okay, thank you very much.
You're welcome. Any other question? Okay, if not, I saw some little bugs in the slide, so I will fix those, and they should be posted a little later tonight or latest by tomorrow morning here at CERN. So thank you very much for listening. Tomorrow we're gonna talk a little bit about the systematic uncertainties that are in this method and some performance observations and another way of tagging pileup jets in the final state, at least for the smaller jets. Okay, so thank you for listening, and I'll talk to you tomorrow again, I guess.